Good afternoon, everyone. Welcome to today's Exploring by the Seat of Your Pants Hangout. My name is Joe Borowski, and I'll be your host for today. If you've been tuning into our events this month, you know that we have been diving deep into climate change, talking to climate scientists and explorers from all around the world, and not only learning about the issue and what it's doing to our planet, but also some of the solutions and things we can do to help mitigate this really trying issue of our times. So I want to give a shout out to Environment and Climate Change Canada, thank them for their support in making these events possible for this month. And then let's get right to the main event. So today we're hanging out with Melinda Webster. Melinda is a polar scientist at NASA's Goddard Space Flight Center. Her work uses a combination of satellite, airborne, field, and model data to study the frozen oceans in the Arctic and Antarctic environments. So she's been involved in several polar expeditions, traveling by aircraft, ship, and snowmobile to collect measurements of sea ice to better understand its role in the Earth's systems. From growing up in small town Oklahoma to being frozen in the middle of the Arctic Ocean, she loves to inspire students to break norms and reach for new possibilities. So Melinda, it's so great to be stealing a little bit of your time today. We're gonna look forward to learning a little bit more about you, and then we'll let the classrooms take it away with some Q&A action.
Fantastic. Thank you so much for having me. I'm really excited to highlight some of the work I've been doing. So let me just get that started right away. Okay, just let me know when you see my screen.
All right, we're nice and full screen.
Okay, great. All right, so I would love to share with you what it's like being a polar scientist at NASA. As you'll see, it's not a clear-cut path, and there's a lot of ways to get to something like this. So before we begin, I'd like to tell you a little bit about myself. Who am I? My name is Melinda. I am a polar scientist, but I've not always been a polar scientist. I actually grew up in Oklahoma. I spent the first 20 years of my life there, and I was not doing any polar science there. In fact, I didn't really do anything involving climate change or science in general. What changed that was I got to volunteer with some scientists and learn about their work, and that motivated me to go back to school and finish my degrees in Seattle. So this was at the University of Washington, and I was learning about oceanography there. And from there, I got involved in polar science, specifically sea ice research. I got a position at NASA's Goddard Space Flight Center just a few years ago, so I made the big leap from going from Seattle to near Washington, D.C. to start my job as a polar scientist. So what does a polar scientist do? That's a really funny question to ask because a lot of people have different expectations of what we do. My mom thinks I'm like Bill Nye the Science Guy. I'm not. Society thinks I'm kind of like a mad scientist. I'm not that either. My boss probably thinks I'm a walking disaster. So there are all these perceptions of what scientists do, and some of them are right, some of them are wrong. What do I actually do? So this is a really nice graph that shows that. My job is a combination of things. So the big part of it is being creative, coming up with new ideas and new interpretation, and reading and writing. That's what I do for the vast majority of my time. The other part of my time, I'm analyzing data. I'm crunching numbers. I'm using math and science to do this, but it turns out you don't have to be an expert in math to do this, which is great because I'm not. The other part of my work is more working with teams, so networking, being on a field expedition and working with others. And that's really my favorite part of my job, is getting out in the field and being able to work with others. The last part of my job is I do a lot of public service. So what does this mean? It means talking with folks like you about the work that I'm doing, but it also means meeting with politicians and showing why science is so important and why we need to pay attention to the ongoing changes on our planet. So in summary, that's what my job's about. But now let's talk about the fun part, the science. So I studied the cryosphere. And the cryosphere is actually a really easy thing to define. It is the frozen parts of our planet. And when you stop and think about that, the frozen parts of our planet are everywhere. They're not just in polar regions. They're on every continent of our planet. And this is really cool. But it's not just limited to the continents, it's constantly changing. You know, you'll have a lot of snow in winter and then you'll have no snow in summer. The cryosphere expands and contracts with the season. It's constantly evolving over time, over short time periods, like on a seasonal basis, to really long-term trends like the loss in Arctic sea ice and the North Pole environment. So this is good to keep in mind when you hear the word cryosphere. This is what it entails. Now, the cryosphere can be defined a little bit differently in saying, okay, well, there are two parts of it. There is the snow part, and then there is the ice part. That's easy to think of. And my area of expertise is on the ice, but it turns out not all ice is created equal. It's not all the same. You have ice that comes out of your refrigerator that you put in glasses of water. That's freshwater ice. The thing that I care most about at the moment is sea ice. This is the frozen part of the ocean. And in today's talk, I'm going to try to convince you that this is the coolest type of ice ever. Okay, so why is it so awesome? Well, I think if you had to step back and say it, it's really the key thing that regulates our climate. It does a number of really important things for the Earth system to help maintain a habitable place and to make sure that we're not too warm and we're not too cold on this planet. So what does it do exactly? Well, its superpower is its high albedo. And albedo is a way to describe how much sunlight is reflected back into space. So we have an example here where you have an ice-covered area. It reflects about 70 to 80% of the light back to space. That's a really large amount. Compared to the ocean only reflects about 7%. So that's a huge difference. That's like wearing a black shirt or a white shirt in a sunny desert. You would much prefer wearing a white shirt so it's not so hot versus a black shirt which is absorbing a lot of sunlight and making you too warm. That's what sea ice does for our planet. Now, it's also important outside of its albedo effect. It's also really important for regulating where our planet warms and where it cools off. So in this figure, I'm showing what the temperature is on our entire planet. The blue colors are where it's cold, the red colors are where it's warm. Because the ice is so reflective, this is helping cool our planet at the poles where it's really important too. Okay, there's also some other things that make sea ice really important, and this has to do with our oceans. So they're one of the big drivers of our ocean currents, and a lot of people are surprised to hear this, but sea ice does two things for our circulation of our oceans. One is that it cools seawater, and colder water is denser or heavier than warmer seawater. And the second thing it does is it makes seawater salty. Salty water is heavier than fresh water, so this causes these water masses to sink and to create this convection, this overturning of the oceans. And that's really, really important for transporting heat to all the right places on our planet. Now, there's one last thing that makes sea ice amazing. And I'm going to play a video, and I want to see if you can see what's going on. It's really unique. And a lot of people tend to overlook this about sea ice. Oops, let me go back. Hang on. Okay, so in this video, which I hope you're seeing, you'll see this little blob moving around. This is a picture of sea ice, and that blob is a living thing in the ice. The reason this is incredible is that this is proof that life can live in an extreme environment like the ice itself. And this gives us clues to what could be happening on other planets and moons outside of the Earth system. So if we're trying to find life on other planets or in other places in the universe, the sea ice environment is the perfect case study to see where they might be living. And that is pretty amazing in itself. Okay, so how do we know all of these fascinating things about sea ice and what's going on with it for climate and what's going on with it for life forms? Well, we go out on the ice, from the boots on the ground to flying in aircrafts to launching satellites into space. We use all of these different ways to measure the ice in different time scales and spatial scales to get as much information as possible. And that's what we really need to do to understand how it works in the Earth system. So one of my favorite things to do for my job is to take an aircraft to high latitudes to take measurements of the ice cover. So we equipped the airplane with a lot of snow thickness and ice thickness instruments. And these are really important for monitoring the changes happening in our environment. So we've seen a loss of sea ice over time. The planet is warming, especially in Arctic environments. It's warming more rapidly than anywhere else. So we're having a lot thinner ice and less extensive ice. And these airborne surveys are really important for gauging that change. Another way that we do it is we go out in the field, but this is extremely risky. So doing field work is challenging. It's an extremely remote environment. So when things go wrong, there's nobody there to really bail you out or help you. It can be really dangerous. The ice can break up. You can fall through the ice if it's too thin. There are polar bears, and those are dangerous. And of course, it's really, really cold. You can get hypothermic, and that can be scary. And oftentimes with these fieldwork expeditions, we only get one shot to get things right. We don't get to do a repeat usually because we just don't have the money to. That's the way things work. So why are we doing this? Why do we take all these risks to go out and try to take measurements? Well, there's a lot of good reasons, I would say. For me personally, it's an adventure. I love going out in the field and learning new things. You know, when you're curious about how the Earth works and what's happening in these environments, being out there is so informative and exciting. And I think what's often the biggest reason to go out and do field work or airborne campaigns or satellite missions is this is really where the groundbreaking discoveries happen. This is enabling new science to be done, and it opens up our understanding in ways that were never possible before. Okay, and then on a personal note, when you're out in the field, your colleagues become family because you're there for months on end. And this is really cool because I can't imagine going out in the field with anyone else than my colleagues. They're wonderful people, and it just makes it so much fun to do this work. And summarizing all of these points together, this really makes this job a passion, and I feel very lucky to do what I'm doing. And I think it would be great for anyone else to get involved if this sounds right up their alley. Okay, so with fieldwork, how do we actually get out in the field, and how do we prepare for these expeditions? There's a lot of things that could go wrong. There's a lot of risks involved. So how do we do it? Well, we come up with a plan, and we have lots and lots of backup plans for when things go wrong. So we have to coordinate what types of instruments are we going to be using? Do we have redundancies in place for when things break? So we might want to bring double the amount of instruments that we need because the first set of instruments may not last as long. We need to identify who the key players are on our team. It's kind of like assembling a sports team or a baseball team. How are you going to choose your all-star team to be successful? You want the expert at pitching. You want the expert at modeling. You know, you want to assemble the strongest team ever so you can be successful in what measurements you're trying to make and conclusions that you're trying to draw. Okay, and then there are some other elements to fieldwork and airborne missions that take place. So identifying what time of year we want to go take measurements, how long we're going to spend in the field, and how much is all this going to cost? Because it can be really competitive to put these ideas together. It has to undergo review. So you don't want to be too expensive. You don't want to be too ambitious. You want to have the perfect Goldilocks scenario where it's not too much and it's not too little. It's just right so somebody thinks it's a solid, doable idea. Okay, so when we're actually out in the field, it can be really difficult. So I often go out in the springtime where it can be minus 40 degrees Fahrenheit, which is the same as minus 40 degrees Celsius at that point. It's just really cold. And it can be difficult to do a number of things simultaneously. So the first three things that I try to do is to stay warm, to breathe, and to see. And it's really hard to do all those three things at once. So in the picture in the upper right, you'll see that my face is all frosted over. That's because I'm trying to stay warm and I'm breathing hard, but my goggles are getting all fogged up. So if I take them off, then I can see, but then I get cold. So it's just this reconfiguration of trying to do all these things at once that you get used to after a while, but it can be hard. Bringing snacks out into the field, they freeze immediately. So you have to keep things close to your body. Batteries and things like that, you have to keep close to your body so they don't get frozen. And so you want your instruments to work. At the end of the day, you really want to get good data, but you also want to be safe. So you're constantly assessing the risk to make sure you're not making a bad decision. Okay, so how do we do this as a team? Well, it really goes back to what you learn when you're really young. You're taught to help others. You're taught to pick up the slack. You're taught to communicate. All of these things are really, really important to being a successful team player in a field expedition, an airborne mission, or a satellite mission. And at the end of the day, it's really important to have fun because we're all human and we're all doing this because we love the work. So it's nice to have fun with it. But I think probably one of the biggest secret weapons to success in the field is candy. This is a great way to make friends, and it's actually a really effective way to boost morale when you're out on the ice for months on end. These little things make a big difference and help your relationships with others. Okay, so after we go on a field campaign, we get to go home happy, but then what happens? Well, the biggest thing is analyzing the data and making discoveries. So the biggest part of my time is spent reading and writing and coming up with new hypotheses and crunching all of these numbers that we collected and trying to make something meaningful and important out of them. So for my work in particular, I've done a full range of stuff where I've been looking at cyclones and storms and seeing where they go in the Arctic. I've been looking at the temperature of the ice and how that evolves over time, going from winter into summer, seeing how quickly it melts and how it's changing. And on the upper right, I've been looking at changes in snow depth on sea ice. So we were able to tie in all these different measurements for a really long time period to see how the snow cover has thinned over Arctic sea ice. And on the bottom right, and this is something I'm pretty excited about, is working with artists to put our science into a beautiful image. How can we take all these numbers and all this dry information and make it really exciting and visually appealing to different people? And so this figure is just showing how complex snow on sea ice can be for the Earth system. And all of these components come together to tell powerful stories about sea ice. So that's something that really excites me in particular about my job is we take all of these numbers and we learn something new. Everything that we're doing, all the measurements we take out in the field are the first of their kind, and it's always adding something new and positive to our understanding of sea ice and Earth as a system. Okay, so that's all I have. I really appreciate you paying attention. I'd love to hear your questions about this work, so thank you.
All right, Melinda, thanks for that awesome presentation, giving us a little glimpse into the life of what it takes to be a polar scientist. I have no doubt that several of the classrooms are pretty excited about that candy part. I think that sounds pretty interesting. Sounds like a good thing to bring out in the field with you.
Absolutely.
All right, well, quick shout out to any classrooms who might be tuning in on YouTube. Use the chat sidebar on the right. Let us know where you're watching from and send in a question or two, and I'll keep an eye out for those. But for now, let's get down to business. Let's start meeting some of our live classrooms. So we are going to go to Independence, Missouri to start. Mrs. Hoxley's got some fifth graders hanging out with her. Let's get that microphone turned on. How are we doing, fifth graders?
Hi, my name is Sin, and my question is, have you ever fallen in the ice? And if you did, how cold was it?
Well, I haven't fallen in the ice yet, but I've been very, very close. So one time I was out on the ice in May, and we were really curious about why the ice looked so dark. And we stopped our snow machines to have a look and to measure the ice thickness to see why it might be dark. And we drilled a little hole and stuck a ruler down in it. And I noticed as we were taking these measurements, the ice started bending and bending and bending. And we realized what was happening. It was about to break. And sea ice is a little different than freshwater ice. It's really elastic. It can bend and you can have waves in it like that. So when we saw it bending, we knew something bad was about to happen. So we hopped on our snow machines and left very quickly. So I haven't fallen in yet, and hopefully I never will.
All right. Sounds like you made the right choice to get out of there.
Mm-hmm.
Okay. Well, let's see. Let's go to Mrs. Tracy's group. They're in San Jose, California. Let's get that microphone turned on. How are we doing, California?
Awesome. Thank
Awesome.
All right. Who's got a question for us?
How do you get water?
How do we get water? So there are a number of ways. We can bring it with us. We can put it in water bottles and just keep it in pockets right next to our bodies. Or if we're out on the ice for a long period of time and it's really, really old ice, we can actually melt that and drink it. So there's two types of ice in the Arctic. There's young ice, which is pretty salty, and then there's old ice, which is really fresh. You could drink the old ice if there's any around. You can't drink the young ice because it's really, really salty and gross.
All right. File that away for later. Avoid that new ice. All right. Good. Let's see. Mrs. Nikolovsky's group, grade 6, is hanging out with us in Canada here in Oakville, Ontario. Let's get their microphone turned on. How we doing, Oakville? Sounds like lots of students hanging out in Oakville, Ontario. Who's got a question for us?
I do. Roughly how long do you stay in the Arctic till you go home?
Oh, that's a great question. So it varies depending on the mission. It can be anywhere from a week, but I have this really exciting field campaign coming up where they're freezing a ship in the ice for an entire year. I will go for 3 months, and that will be the longest that I stay out, but some people are going for 5 months, and I've heard of some that have even stayed out for over a year. So that's not unheard of, but for me, I try to stick to 2 to 3 months.
All right. Great question from Oakville, Ontario. Mrs. Wong's group, they're in Toronto, Ontario. Looks like some 8th graders hanging out with us. Let's get that microphone turned on. How we doing, Toronto?
We're good. We're good. Okay, I have a question for you. Have you ever had any groundbreaking discoveries while out on the field?
Yeah, we have. Probably one of the really exciting ones was in 2011. We were on a field cruise in just north of Alaska. And, you know, this is kind of a funny discovery. There are different people that go on these cruises. There can be biologists, there can be people who are ice experts or oceanographers. I was out with ice experts and we were taking these measurements. We're like, wow, the water's really green. This is kind of gross. The biologists were going wild. And we were trying to figure out what the big deal was because we're in this ice-covered area. And what we had discovered was this massive phytoplankton bloom underneath the ice. And the reason this is really exciting and new is the understanding was phytoplankton blooms happen in open ocean where you get a lot of light going into the ocean, not when there's ice blocking all that sunlight. And so this was exciting because perhaps we've been underestimating how productive our oceans are if these under ice phytoplankton blooms are a big thing. And ever since then, there's been regular cruises going out and taking these similar types of measurements, and it's really revolutionized how we estimate the productivity of our oceans. So yeah, that was one cool discovery for sure.
All right, very cool. I think that's pretty much the best thing about science is that you can make these really cool discoveries, find things you didn't expect. You can go out with 100 questions and come back with 100 or 1,000 more. So I think that's pretty cool.
Absolutely.
All right, awesome.
Oh, I can't hear you.
There we go. You should be able to hear me now. yeah, I want to give a shout out to Mrs. Anderson. She's joining us from Switzerland. She's checking things out for some classrooms over there. So I'm going to turn her mic on and see if she wants to ask a question.
Hello. I don't have a question.
Hello.
That's okay. Well, thanks for tuning in from Switzerland. It's always great to have two continents hanging out in an event.
Yes.
All right, very cool. Well, let's make a swing back through. Let's go to Mrs. Hawksley's class and see if they have another question for us.
Go ahead, CJ. Sorry, we weren't ready. He's coming.
Hi.
Hi. My name is CJ, and my question is, what time did you start, and how was you able to get into discovering ice and stuff?
Yeah, that's a great question. So I didn't realize I wanted to do this until I was about 22 years old. I went to college when I turned 18 for a couple of years, and I wasn't sure what I wanted to do. So I left without finishing and got a job and traveled the world. And then when I had the opportunity to help some scientists with their fieldwork and realized that you could get paid to do this stuff, I was like, oh, I want to go back to school and try to do this. And so then I went to the University of Washington, finished my degrees, and after that, everything just fell into place. So I think when you figure out that you're really excited about something, it's cool to pursue it because it usually works out at the end of the day.
All right, great question. So I got a question coming in via YouTube, and they are saying that they've heard that you have to eat more when working in the colder conditions. Is that true, and why?
Oh, yeah. Well, I eat a lot, so it's hard for me to gauge. I think we eat a lot, probably more because there's just food around us, and at the end of the day, it's kind of something to do. Yeah. It really depends on what type of work you're doing as well. So if you have field campaigns that are really rigorous, you're going out and taking measurements for 7 hours a day in the cold, yeah, that's really draining and you have to eat a lot more calories. But if you're flying on an airborne mission where you're just sitting down for 8 hours a day, you don't necessarily burn that much energy. It's tiring, but you're not as active, so you don't have to eat as much. So it depends on the mission.
All right, so those plane missions, then it's more of like a candy for comfort or something.
Oh, yeah, absolutely.
All right, awesome. Let's swing back to Mrs. Tracy's class. Your microphone is on again.
No, it's your question. Thank you.
Is it certain fish that get to go in ice, or all of them?
Certain fish that get to go in ice?
Yeah.
Yes.
Yeah, so there are certain fish that live in polar environments, that live in polar oceans. I don't know if they actually ever get up into the ice because they're quite big. There are these really, really small microscopic living organisms that live in the ice. Like what I showed was phytoplankton that go through these little, they're called brine channels. There are these little cracks in the ice full of salty solution. So the microscopic stuff can live in the ice. The fish, not so much, but they eat those microorganisms. So they're connected. They're really important that the microorganisms are there and available for the fish to eat.
All right, very cool. We had a photographer who joined us last week, I think it was, and this is a different kind of ice. He was photographing glaciers, and he had some really cool footage of worms that live inside of the ice and were moving through the ice. That was pretty cool.
That's awesome. Yeah. Cool.
All right, let's go back to Mrs. Nikolowski's group. Your microphone is on.
Hello. What's your coolest discovery and where was it? Like where in the web?
My coolest discovery. Well, let's see. I think my coolest discovery was in 2014. Well, actually, I took the measurements in 2012, and it took me 2 years to analyze the data to come up with the conclusion. And the most exciting thing I found was the snow on top of the sea ice was thinning. And that's really important because it tells us how the surface is changing. So I talked about this albedo effect, it being super reflective. If there's less snow, it's not as reflective. And so that was a really important discovery that nobody had ever yet connected those dots. That was really exciting and got a lot of attention by media and policymakers.
Yeah, it's definitely something that we have to think about. We need that sunlight reflecting, and our polar regions are, is it what, about double, heating up twice as fast as other regions?
Absolutely, yeah.
Yeah, all right. Mrs. Wong's group, your microphone is on again.
Hello.
Hi.
Hi. So our question is, how do you distinguish between young ice and old ice?
Oh, that's a fun question. So there are many little characteristics about these ice types that can help tell them apart. So one obvious one is its thickness. Young ice tends to be thinner, anywhere from like this much to about 1 meter. Old ice tends to be 1.5 meters to can be even 8 meters thick. It can be really, really thick. And also the topography, or how rough the surface is. So when you think about sea ice, it's not static, it's moving with the wind and ocean currents, and it's colliding with one another and coming apart. So it gets really deformed the older it is. And so its surface can be really rough and hummocky and have ridges, or they look like miniature mountains. Those are telltale signs that the ice is generally older. For young ice, it hasn't had as much time to get deformed, so it's often smoother. And if it has been deformed, the blocks of it are very angular versus stuff that survived a summer melt season and has melted a bit and become rounded. So there are these characteristics that help define and help identify what these ice types are.
All right, very cool question. So we do have some more time. So what I'm gonna do is, classrooms, if you want another question, either give a wave or send someone right up to the camera, and that'll be my clue that we need to come back to your group. Oh wow, we got someone really close to the group. Well, I guess we better go there first. They need business.
Okay, so we have another question. How
Sure.
do you convince people that climate change is in fact real?
Yeah, that's a great question. So lucky for me, it's really easy because I just pay attention to the facts. I look at the data and it undergoes peer review to make sure that the conclusions are indeed true, and we lay this out for policymakers. So it's not our job to convince policymakers what to do with that information, but our job is to make sure that's the highest quality information available for people like you, for politicians, for policy making decisions and things like that. When it comes to convincing people that the science is real, all of our data and all of our results are publicly available. That's mandatory. So if anyone wants to put up a reluctance to believe it, they can always redo the analysis themselves. We have to make everything reproducible. That's just the way science works. So those mechanisms are in place to show that, hey, this is strong science. Hey, this is indeed the conclusion and the fact. So my job's pretty easy because all those things are set in place.
All right, I think I see someone pretty close in Mrs. Tracy's class. We better stop in there and check.
How do fish see plankton?
How do we, what was your question?
How do fish see plankton?
Oh, yeah. So there are different ways we can look at fish and zooplankton and phytoplankton. And one of the things we do, especially from research ships, we'll go out in the middle of the Arctic and cut a hole if there isn't one, or we'll go to where an open spot in the ice pack is. And we'll drop this thing called a CTD. It's this big device that goes down in the water, and it measures the salinity, it measures so how salty the ocean is, it measures the temperature and the depth at which it is, and it collects samples of the water that it can run through this thing called a fluorometer. And what the fluorometer does is it measures how green the water is. So that's a measure of how productive it is from phytoplankton in it. Another thing that we do is we'll drag nets behind the boat and actually count what zooplankton are in it, like what types, the species. and how many of the species are there. So there are different ways to measure the phytoplankton, the zooplankton, and the fish.
All right, I think I see someone up close in Mrs. Hoxley's class, so we'll check in and see if they have a question, a last question for us.
Cool.
Hi, my name is Trinity, and my question is, what's the most dangerous place that you visited?
Oh, that's a good question. Well, falling in the ice at one time was pretty dangerous, but there have been other times too. I think just in general, there can be some danger with polar bears. And if you're just not paying attention, if we try to make it where there will be polar bear guards with us, so somebody who is constantly on watch, keeping out. And in certain times of year, especially near northern Alaska, there's a crack in the ice that forms every spring. It breaks away, and all these seals show up, and then all the polar bears show up. But if it takes a while for that crack to happen, all these polar bears show up hungry. So we just have to be extra diligent and extra aware of our surroundings to make sure we're not putting ourselves in a bad situation.
All right. Let's see. We'll swing back to our group, Mrs. Nikolowski's group. I know they probably have another question, so let's see.
Yes, thank you. How many years have you been doing this job?
Ooh, I've been doing this job. I've been researching sea ice for over 10 years now. Yeah.
All right. Well, I think we have time for one more question. So I'm going to need to see a classroom that really wants that last question, if they do have one more question. Let's see.
See lots of hands.
All right. I'm going to keep the mic on at Mrs. Nikolowski's group because I see a ton of hands waving just below the camera. All right, here comes someone.
Where was the closest place you've ever been?
The closest?
The coldest.
Coldest. Oh, so that was in Reykjavik, which was also formerly known as Barrow, Alaska. And that got down to minus 47 degrees Celsius, and it was really windy. So the wind chill was a lot colder than that. I was pretty cold also because I was riding on a snow machine into the wind. So it seemed very, very cold. And I actually got a little bit of frostbite, but it's fine now.
All right. Well, classrooms, thank you so much for hanging out with us today. As per usual, your questions were awesome. So big pats on the backs for everybody. And Melinda, thank you so much for letting us steal some time out of your day. I know lots to do and lots to think about. So thanks for hanging out with our classrooms today.
Well, thank you guys so much. I really enjoyed your questions. So come do polar science.
All right. I'm going to turn all the microphones on, boys and girls. If you want to get nice and loud, it's time for a goodbye and thank you. Always so good at that and ready. Melinda, again, thank you so much. Hopefully we'll see you in the future for another hangout. And to all the classrooms, have a great day, and we'll see you for another Explore My Seat Your Pants in the future. Thanks, everyone.
Thank you. Bye.